Hey guys, what's going on? So today we are going to cover quantized momenta for our real scalar fields, and then we're going to start to introduce the idea of complex valued scalar fields, and that's where we're going to start talking about antiparticles and particles. So let's go ahead and get started. Make sure to hit that like and subscribe button. One thing I want to note also is that now for just $10 you can become a member and get any of the content on this page. I like the progress of this channel, so I decided that I was going to just make one subscription, and it was just going to be $10, nothing 25 or $50 or anything like that. And with that $10 donation, you will be able to access everything on here. I'm making a website, which you'll be able to access also. I'm also compiling all these notes into some nice LaTeX documentation, and that's going to be available to you guys as well. So with all of that out of the way, now let's go ahead and get started. So we're talking about quantum momenta now. So in the last video we talked about the Hamiltonian for our fields. Right, so you have this field. This field is a scalar field. The scalars are vibrating. Those vibrations they're vibrating at certain frequencies, and those frequencies can get annihilated or created by these operators. Okay, so now in special relativity we deal with energy and we deal with momentum. So in the last video we talked about energy. That was our Hamiltonian. So we're going to do this very similar thing now, but with our momentum. And so we did for our momentum we have this as our definition, right? So this is our momentum density, right, because it's going to be put into some volume, and then when we integrate the volume over that density, we get the total momentum. So we have a field. Our field is it's a field of space and time, and we can think of this as a field existing. It's sort of like a density field that exists in some volume. I'm going to erase that really quick and reduce the thickness of my pen here. So we have some volume. We're integrating over that d3x volume, and that we have our field. Our field in here it takes values everywhere, right? So it takes this could be 1.5 over here, it can be 2.6 over here, it can be 7.1 over here, it can be 21 over here. We have this field. The field, again, it's a three-dimensional field. Also in time makes it a four-dimensional field. But the idea here is that this is what our field is, and we can calculate a total momentum of our field within that volume. Okay, we did the same thing with energy in the last one. We didn't really have this visual in the last video, but the idea here is that we're integrating over some volume, okay, of our momentum density. So our momentum density is this thing, right? Because we took if you take the derivative of our Klein-Gordon-Lagrangian with respect to the time derivative of our canonical position variables, multiply that by this guy here. Well, this guy here is the spatial derivative. That's just a gradient, and then this guy here, we said earlier also that was the canonical momentum. Okay. So we put this thing into our integral and we get this, and so now we can calculate this thing because we know pi and we know this thing here. We know the gradient of our field, and so the gradient. So here's the gradient of our field. Here's pi, canonical momentum, and those are these right here. And then we're going to take those. We're going to take 3 and 4 and we're going to place them into equation 2, which is right here. And when we do that, we have this beast of burden. This thing here is going to get turned into this when we do. So this thing here, when we do all this multiplication out, right? So this thing here gets multiplied by this over here, then this gets multiplied by this, and so forth. And when we do that, we get equation 6. Okay. So we're at equation 6. Again, we can recall the rules of Fourier analysis. And when we do that, we get these. So we talked about Fourier analysis last time. Again, really the idea here is that you have a wave, the e to the negative I anything is a wave at a frequency of that anything, right? So this is the frequency along the x direction, okay? And the frequency, whatever this is, we're going to have a Kronecker delta, okay? This is Fourier decomposition, right? So we decompose this wave in frequency space to have this thing, to be this thing right here. This is a Kronecker delta at some particular frequency along the frequency axis. So just to picture this a little bit, because this video is going to be probably a little bit shorter than other videos. So we have some wave, and we haven't really gone over Fourier analysis. I'm sort of doing a rundown, a very brief rundown of this. But this thing has a frequency, right? This thing has a frequency. This frequency is also related to the wavelength. So we have some frequency F, say, or frequency K, right? Actually, let's make this a little bit more literal. K is our frequency. It's our spatial frequency. And this thing, this wave, can get converted using Fourier analysis into a spike. And that spike exists on the k-axis, or frequency. It's whatever the frequency this is, the value of that frequency is going to be right here, and we'll have a spike right here. So if we have a wave then that has multiple, looks a little bit more complex. Well, this thing can be decomposed into more simple waves, right? So it might be decomposed. We can decompose it into something like this, and then another one like this. And what this is going to do is our waves are in frequency space. This is going to look like, again, this is very crude and rudimentary, but this is going to look like we're going to have a spike. Oop. We're going to have a spike. Oop. Let's have this be black again. We're going to have a spike for one of our waves, and then we're going to have a spike for another wave, say over here, depending on what those frequencies are. Okay? That's the Fourier decomposition. Right? So here are those spikes, and the integral, so this is the sum over our complex waves, is going to be equal to the spike times this normalization factor. And then this guy here, right, so this spike is going to cause k prime to collapse to k, and so omega prime is going to collapse to omega. When we do that, omega minus omega is going to be 0, which brings this to 1. And then this omega, this is going to be 2 omega, so we get this minus 2 I omega t. Alright, so we take equation 7 and 8 now, we're going to plug them into equation 6, which is this thing, is B straight here. So things get ugly before they get nice in physics, it's often the case. So when we do that, we get this giant thing. You could pause the video if you want to see this in action. But I looked over this. If you catch something, let me know in the comments. This here and this here, right? So this here, A, right? So this is A times A, or which is right here, A times A, and then A dagger, A dagger, and so forth. And then wherever we see this thing here, which are these guys over here, we just literally plug these things in. All right, and when we do that, then we'll say that the K prime is going to collapse to K, which is what the Kronecker delta does, and so then we get this here. This here, well, this thing, these two guys are the complex conjugates of each other, right? So integrating over this is actually going to take us to 0. So because we have this negative I here and this positive I here, and then A not daggers, A daggers. So these are actually complex conjugates over each other. So integrating over these things is actually going to bring us to 0. And so we're just left with this bit right here. Okay? And so that's this part up here. And then from here to here, then we can actually say this is a commutation relationship, right? So the commutation relationship here is, we need this 1/2. We need to keep in mind this 1/2 too, because this is 1/2 a dagger minus a dagger a. And then we're subtracting that from this thing, which is a dagger a. And so that is going to be a dagger a 1/2 a dagger a, right? Because it's this minus this bit, well, with this 1/2 minus plus, actually, right? Plus because we have this minus sign out here. So that's going to be plus 1/2 a dagger, right? And that's this right here, right? With excluding this thing that gets left out here. So I don't want to totally exclude it, but the idea again is that, so this k here is this k here, and then the rest can be drawn out, right? So this thing here is this minus half of this. Okay. This we're integrating over symmetric integral again. When looking at this, so I can erase. I'll just erase this. I'll erase this here. Erase these here. When we look over this thing, this is we're integrating over a dagger minus a dagger a. Right. Well, these two things are the same thing, right? So it's this thing minus this thing. Well, so that's just going to go to 0. So integrating over that is going to take us to 0. All right. So we're left with this then, that our canonical momentum is this thing. This looks an awful lot like our energy, with the exception of our k in front of here, the k in front of here, not the omega. All right. So here we have it. So we've developed our canonical momentum for our field, our canonical energy for our field, and all the necessary commutation relationships between our creation and annihilation operators. This is just for the Klein-Gordon the real scalar field that has a Klein-Gordon relationship to it, or that has a Klein-Gordon fields of motion, or equations of motion. And so we have this flowchart that we're going to keep on coming to. This flowchart is it's going to depict what we've been going through for the last few videos, so that we can so that this methodology can sort of stay at the forefront of our minds. And we always want to know where these things come from as well. So constantly reminding ourselves how we got to each point here is going to help us. It's going to give us a broad canonical overview of quantum field theory as well. Okay. So we started with canonical position variables and canonical momentum variables. Right? That was position was x, momentum was p, and then from there we established the Heisenberg uncertainty principle. And when we did that, we were able to then use the Heisenberg uncertainty principle for our fields, right? Because remember, that was phi, this commutation relationship right here. And when we did that, we found these guys here. This was our quiz. This is sort of the first steps we took when we established our quantum fields. Right? The idea of the fields, remember, was bringing Q. So this thing was Q, this thing was P, bringing these things to a continuum where this turned to x, where this thing turned to that, and p of turned to x and t. Right. That was really the step. That was really the step in making these fields, right? Because they're now they're functions of position and time, as opposed to being discrete springs. Okay. And then we went from here to here, and the way we got to here is we implemented some classical field theory. We established our Hamiltonian. We wrote it in terms of our Lagrangian and so forth, and we wrote down our momentum as well. Our momentum. Both of these guys come from the stress energy momentum tensor. So from these two guys, we were able to use these relationships and these relationships to establish our quantized energy and momenta. So this guy here is our quantized energy. This guy here is our quantized momentum. Notice really the only difference here is this omega and this k. All right, which makes sense, right? Well, this is energy. This is going to have the temporal component, the temporal frequency component. This is going to be our spatial frequency components. This is our momentum. And then we saw again what our creation annihilation operators did for energy of our field, right? So they raised and lowered energies, right? Okay, this is the general workflow for how we generate quantum field theories, okay? And we're going to keep on adding to this diagram as we continue. We're going to now talk about, at this point, we're now going to start talking about complex valued scalar fields. And then we'll move on to spinners. But so I just want to read this really quick. So everything is going to flow from this diagram here. When we start dealing with spinners, vectors, and tensors, these things are going to get more complicated because we'll need to start keeping track of more indices, right? Vectors in three-dimensional space have indices. Right now, we're just dealing with scalar fields. They don't have any indices, right? All they're just these vibrating numbers that make up that constitute some field. All right, and when it comes down to the brass tacks of things, all we're going to need is a Lagrangian and a pair of canonical variables, okay, to get all the dynamics that we need from these. This is known as canonical quantization. This is the canonical quantization theory of quantum field theory, essentially. And we're going to really get into this, and then we're going to move on to path integrals. We might interchange between them a little bit because we want to keep both path integral formulation and canonical quantization formulation in the forefronts of our minds as well. But we're going to continue building on this diagram throughout because my aim is to show how we can come to understand things like correlation functions in terms of this flowchart, generators, propagators, and so forth. Within this much larger framework of things. So let's now move on to complex scalar fields. We're going to recall the Klein-Gordon Lagrangian. This is what our Lagrangian looked like. So, and here we only allowed our scalar fields to take on real numbers, right? So these phi's, we only really allowed them to take on real numbers, okay? Not complex numbers or anything like that. But nothing, however, should stop us from allowing our field to take on complex numbers, heck, even quaternionic or octionic numbers, right? We could develop a theory. We could develop a quantum field theory, a scalar quantum field theory that in which the scalars are octonions, right? Those are 8-dimensional numbers, or quaternions. Those are 4-dimensional numbers. Those are very complex things. We're not going to talk about octonionic numbers quite yet. However, they are an interesting thing. And implementing them in quantum field theory is actually quite interesting. You know, I've played around with them a lot in quantum field theory, and I think we might actually go into that. It's a very theoretical thing, but it's super interesting. All these number systems that should work for our system, right? in our system of real numbers, it was easy to make sense of what these represented, intuitively. They represented numbers that fluctuated at every point in space-time at a particular frequencies, which were given to us by raising and lowering operators, or creation and annihilation operators. By introducing complex numbers, then we add a new whole sort of dimension to the picture here. This new dimension is going to be introducing the concept of particles and antiparticles. So let's talk about that. For our scalar fields, we now allow for the dynamics of complex numbers. This means that we're going to change our Lagrangian to look something like this. This looks an awful lot like our Klein-Gordon equation. We don't have the 1/2 in here. That's just a number that can be absorbed into our scalars. So we're just going to keep everything very straightforward. In flat space, in flat special relativity, we have our Minkowski metric. Okay, and then we have this thing right here and this thing right here. And when we do our Euler-Lagrange equations, we get these two things here. And from these are Euler-Lagrange equations. What these are going to lead to, we've seen these before already, is that we have two. Now we have these. This is a Klein-Gordon equation. We've seen this already. This is a Klein-Gordon equation also. So what we have here are two non-coupled now differential equations. They're not coupled because we don't have a phi bar term in here, right? We don't have a phi bar term in here. It's not in there, right? Our phi bars are, these are complex. These are the complex conjugates of phi, right? So if phi is a number, it's 1 plus I. Phi bar is going to be 1 minus I, right? And there's no coupling of, in this equation, there's no coupling of phi with phi bar. Likewise, there's no coupling of phi with phi bar in this equation as well. So we have, they're not coupled, okay? And they describe dynamics that are now complex value functions, right? So these are space-time points that vibrate this is according to the dynamics of the Klein-Gordon equation. And then these are space-time values that vibrate according to the dynamics of the Klein-Gordon equation, right? These, however, they're not coupled because we don't see cross terms in either one of these equations. So in the next few videos, we're going to cover this question a little bit more mathematically. What I'm trying to do here is I'm just trying to set the intuitive framework to sort of lay that down so that we can understand what these mean. And so because these two things are not overlapping, they have their own dynamics to them. And because they have their own dynamics to them, we can really call them two different types of fields, right? One field we're going to call the real field. I don't really call it the real field because in some sense we just have the complex conjugate of that field, right? So instead of maybe calling this real, we can call this we just put a charge on it. And so what I did here in quotes is positively charged particles and negatively charged particles, right? So we're introducing this idea of charge, okay? It's not, I put them in quotes because we have no strong ties yet between identifying these two fields as being positively or negatively charged. But what we'll find later is that we can use this language to organize our thoughts around these two fields, okay? So we have two fields. Two fields have independent dynamics from each other. They're not coupled. Those two fields, therefore, have to correspond to two different types of particles. One is the opposite of the other, or we can sort of call it the complex conjugate of the other, all right? And the dynamics for one, and this is the dynamics for the other. This is the canonical momenta for that field, and the canonical momenta for the other field. Now you can see here that the canonical momenta of phi bar is phi, that is the temporal derivative of phi. So this is this is interesting, right? So we have a phi bar here. So the canonical momentum of this field is given to us by taking the Euler-Lagrange equations with respect to phi bar, not phi. Okay. Likewise, here we have phi and not phi bar, which gives us the phi bar out here. Okay, these particles we're going to say are opposite to each other. More technically, they're complex conjugated. They're complex conjugates of each other. And again, we're not dealing with spin yet. Spin is it's a whole new beast, where it's going to take us a while to get to spin and to the Dirac equation and all that stuff. But they're going to introduce more degrees of freedom, spin fields of vibrating into other spin fields. We're not going to talk about that yet. In some textbooks, we might read these particles, these phi particles, also as type A and type B particles. It's just nomenclature, okay? So with that being said, we're now going to get into these types of fields, right? So we're now going to talk about, so we went from real, we said, okay, we had this field, actually, let's just recap it again really quick. We had these guys here, right? These were the discrete, this was the discrete case. This is when we talked about our springs. All right, and then we said in the continuum limit, we now go to this, where I, instead of talking about individual masses on springs, we talk about now points in space, a continuum of points in space. So this is space-time. So functions on space-time. And then now we're going to say, well, this thing is real. Well, it can also be complex, right? So we can also have complex, how do I want to do this? We can also have I'll just say it like this. Now we have phi x of t and phi bar of x and t, where these are complex conjugates. All right. That's going to be what we're going to focus on next. We're then going to talk about the number operator, because really fundamentally when it comes down to physics, we're looking at small volumes or fields in these small volumes. We want to be able to know how many particles are in some volume, right? We want to be able to know that we have some particles with some, these are, say, those are the green ones here are particles, and then we have the oppositely charged particles being the red ones. Say we want to count the number of particles in some volume, okay? So we're going to need to introduce the number operator. So the number operator is going to tell us the number. We have our Hamiltonian again, it's going to tell us the energy. We have momentum operator is going to tell us the momentum of the canonical momentum of the fields in this volume as well. All right. So with that being said, I hope you like this kind of content. Make sure to hit that like and subscribe button. You can support me here on YouTube by becoming a member, again, just for $10. You can also support me on Patreon, again, just for $10 there as well. So with that being said, I'll see you guys in the next video.